A topological insulator is a material with trivial topological order that behaves as an insulator in its interior but whose surface contains conducting states, meaning that electrons can only move along the surface of the material. However, the conducting surface is not the unique character of topological insulator, since the ordinary band insulators can also support conductive surface states. What is special is that the surface states of topological insulators are symmetry protected by particle number conservation and time reversal symmetry. In the bulk of a non-interacting topological insulator, the electronic band structure resembles an ordinary band insulator, with the Fermi level falling between the conduction and valence bands. On the surface of a topological insulator there are special states that fall within the bulk energy gap and allow surface metallic conduction. Carriers in these surface states have their spin locked at a right angle to their momentum. At a given energy the only other available electronic states have different spin, so the U-turn scattering is strongly suppressed and conduction on the surface is highly metallic. Non-interacting topological insulators are characterized by an index similar to the genus in topology. The protected conducting states in the surface are required by time reversal symmetry and the band structure of the material. The states cannot be removed by surface passivation if it does not break the time reversal symmetry, which does not happen with potential and/or spin orbit scattering, but happens in case of true magnetic impurities. Prediction and discovery. Time reversal symmetry protected edge states were predicted in 1987 to occur in quantum wells of mercury telluride sandwiched between cadmium telluride and were observed in 2007. In 2007, they were predicted to occur in three-dimensional bulk solids of binary compounds involving bismuth. A 3D strong topological insulator exists which cannot be reduced to multiple copies of the quantum spin Hall state. The first experimentally realized 3D topological insulator state was discovered in bismuth antimonide. Shortly thereafter symmetry-protected surface states were also observed in pure antimony, bismuth selenide, bismuth telluride and antimony telluride using ARPES. Many semiconductors within the large family of Huesler materials are now believed to exhibit topological surface states. In some of these materials the Fermi level actually falls in either the conduction or valence bands due to naturally occurring defects, and must be pushed into the bulk gap by doping or gating. The surface states of a 3D topological insulator is a new type of 2D e.g. where the electron's spin is locked to its linear momentum. Fully bulk insulating or intrinsic 3D topological insulator states exist in B-based materials. In 2012 several groups released preprints which suggest that samarium hexaboride has the properties of a topological insulator in accordance with the earlier theoretical predictions. Since samarium hexaboride is an established condo insulator, that is a strongly correlated electron material, the existence of a topological surface state in this material would lead to a topological insulator with strong electronic correlations. Stannern is a theoretical topological insulator which may display superconductivity at its edges above room temperature. A study published in July 2014 of Nature magazine demonstrates that magnetic components, like the ones in computer memory, can be manipulated by topological insulators. Properties and applications. The spin momentum locking in the topological insulator allows symmetry-protected surface states to host major RNA particles if superconductivity is induced on the surface of 3D topological insulators via proximity effects. The non-trivialness of topological insulators is encoded in the existence of a gas of helical Dirac fermions. Helical Dirac fermions, which behave like massless relativistic particles, have been observed in 3D topological insulators. Note that the gapless surface states of topological insulator differ from those in the quantum Hall effect. The gapless surface states of topological insulator are symmetry protected, while the gapless surface states in quantum Hall effect are topological. The Z2 topological invariance cannot be measured using traditional transport methods, such as spin Hall conductance, and the transport is not quantized by the Z2 invariance. An experimental method to measure Z2 topological invariance was demonstrated which provide a measure of the Z2 topological order. References: A. B. Kane, C.L. Meal, EJZ2 topological order and the quantum spin Hall effect. Physical Review Letters 95, 146802. ARZIV, condition @/05065881. Bibcode, 2005 PHRVL 95N6802 KDOI, 10.1103/Phys Rev Let 95.146802. Jiang Cheng Guai and Xiao Gangwen Tensor Entanglement Filtering Renormalization Approach and Symmetry Protected Topological Order Phys. Reverend B80, 155131. Pullman, F. Berg, E. Turner, R.E.M. Oshikawa, Masaki. Symmetry Protection of Topological Phases in One-Dimensional Quantum Spin Systems. Phys. Reverend B85, 075125. ARZIV, 0909.4059. Bibcode, 2012 PHRV B85G5125P DOI, 10.1103/Phys Rev B85.075125. Zai Chen, Jiang Cheng Guai, Xiao Gangwen, Classification of Gapped Symmetric Phases in 1D Spin Systems Phys. Reverend B83, 035107. Zai Chen, Jiangxin Yu, Xiao Gangwen, 2D Symmetry Protected Topological Orders and Their Protected Gapless Edge Excitations Phys. Reverend B84, 235141, th. G. A Ma 1/4 layer Groening, H. A. Weirdemmer 1/4 layer, Random Matrix Theories in Quantum Physics, Common Concepts. In Physics Reports, Volume 299, 1998, pages 189–425. Pankratov, O. A. Pakhomov, S. V. Volkov, B. A. Supersymmetry and heterojunctions, band inverting contact on the basis of PB1XSNXT and HG1XCDXTE. Solid-state communications 61, 93–96. Bibcode, 1987 SSCOM 61. 93P DOI, 10.1016/0038-1098, 87, 90934-3. Car Paragraph Nig, Marcus. Widman, Stefan. Bra 1/4 Ni, Christoph. Raff, Andreas. Baumann, Hartmut. Molenkamp, Lawrence W. Qi, Xiao Liang. Zhang, Shocheng. Quantum Spin Hall Insulator State in HGTE Quantum Wells. Science 318, 766 €770. ARZIV, 0710.0582. Bibcode, 2007 Sci. 318 766 KDOI, 10.1126/Science 1,148,047. PMID 17,885,096. Retrieved March 25, 2010. Fu, Liang. C. L. Kane. Topological Insulators with Inversion Symmetry. Physical Review B76, 045302. ARZIV, condition @/06111341. Bibcode, 2007 PHRV B76D5302F DOI, 10.1103/Phys Rev B76.045302. Retrieved March 26, 2010. Shuichi Murakami. Phase transition between the quantum spin Hall and insulator phases in 3D, emergence of a topological gapless phase. New Journal of Physics 9, 356 €356. ARZIV, 0710.0930. Bibcode, 2007 NJPH, 9356M DOI, 10.10889356. ISSN 1367-2630. Retrieved March 26, 2010. Kane, C.L. Moore, J.E. Topological Insulators. Physics World 24, 32. Xie, David. Dongqian, Andrew L. Ray, Yuki Xie, Yusan Ho, Robert Kaver and M. Zahid Hussain. a topological Dirac insulator in a quantum spin Hall phase. Nature 452, 970 Euro 974. AR-ZIV, 0902.1356. Bibcode, 2008 Nature 452 970 H doi, 10.1038/Nature 06843. PMID 18,432,240. Retrieved 2010. Hussain, M. Zayed. Kane, Charles L. Topological Insulators. Review of Modern Physics 82, 3045. AR-ZIV, 1002.3895. Bibcode, 2010 RVMP. 82.3045H doi, 10.1103/Rev mod phys 82.3045. Retrieved March 25, 2010. Shadov, Stanislav. Xiaoliang Qi. Jar 1/4 RGEN Car 1/4 Blair. Gerard H. Fetcher. Claudia Felser. Shocheng Zhang. Tunable multifunctional topological insulators in ternary Huesler compounds. Nature Materials 9, 541 Euro 545. AR-ZIV, 1003.0193. Bibcode, 2010 Nat-Ma. 9541C doi, 10.1038/Mat 2770. Retrieved August 5, 2010. Lin, Xin. L. Andrew Ray. Yuki Xia. Zhu. Shuang-Jia. Robert J. Caver. Arun Bansal. M. Zahid Hussain. Half-Huesler ternary compounds as new multifunctional experimental platforms for topological quantum phenomena. Nat-Meta 9, 546 Euro 549. AR-ZIV, 1003.0155. Bibcode, 2010 Nat-Ma. 9546 L doi, 10.1038/Mat 2771. ISSN 1476-1122. PMID 20512153. Retrieved August 5, 2010. Xie, D. Weixia, D. Qian, L. Ray, F. Meyer, J. H. Deal, J. Osterwalder, L. Patty, A. V. Fedorov, H. Lin, A. Bansal, D. Grau, Y. S. Hoare, R. J. Caver, M. Z. Hussain. Observation of time reversal protected single Dirac cone topological insulator states in B2TE3 and SB2TE3. Physical Review Letters 103, 146401. Bibcode, 2009 PHRVL 103N6401H doi, 10.1103/Phys Rev Let 103.146401. PMID 19905585. Retrieved March 25, 2010. No, H.J. H.Co., S.J. O, J.H. Park, H.D. Kim, J.D. Ramo, T. Valla, T.E. Kidd, P.D. Johnson, Y-Hu and Q. Lee. Spin-orbit interaction effect in the electronic structure of B2TE3 observed by angle-resolved photoemission spectroscopy. EPL Europhysics Letters 81, 57006. AR-ZIV, 0803.0052. Bibcode, 2008 EL, 8157006 and doi, 10.120981/57006. Retrieved April 25, 2010. Abishie, D. Xia, Y. Qian, D. Ray, L. Deal, J. H. Meyer, F. Osterwalder, J. Patty, L. Chekovsky, J. G. On, N. P. Fedorov, A. V. Lin, H. Bansal, A. Grau, D. Hoare, Y.S. Caver, R.J. Hussain, M.Z. A tunable topological insulator in the spin helical Dirac transport regime. Nature 460, 1101 Euro 1105. AR-ZIV, 1001.1590. Bibcode 2009 Nature 460.11018 doi 10.1038/Nature 08234. PMID 19620959. Zhu al. Observation of topological surface state quantum Hall effect in an intrinsic three-dimensional topological insulator. Nature Physics 10, 956 doi 10.1038/NPHYS 3140. Eugenie Samuel Reich. Hope's surface for exotic insulator. Nature 0, B. K. Sun. V. Galitsky. P. Coleman. Topological Condo Insulators. Physical Review Letters 104, 106408. AR Ziv, 0912.3750. Bibcode, 2010 PHRVL 104J6408D doi, 10.1103/Phys Rev Let 104.106408. Retrieved January 6, 2013. Weird materials could make faster computers. Science News. doi, 10.1038/Nature 13534. Retrieved July 23, 2014. http www.nature.com Journal 7510 Nature 13534 HTML, Fu, L. C. L. Kane. Superconducting proximity effect and Majorana fermions at the surface of a topological insulator. Phys. Rev Let 100, 096407. AR Ziv, 0707.1692. Bibcode, 2008 PHRVL 100 I6407F doi, 10.1103/Phys Rev Let 100.096407. Retrieved 2010. Topological superconductivity and Majorana fermions in metallic surface states. Andrew C. Potter, Patrick A. Lee, Phys. Rev B85, 094516 AR Ziv, 1201.2176, Xie, D. D. Xie, Weixia, L. Ray, D. Qian, A. Pal, J. H. Deal, F. Meyer, J. Osterwalder, C. L. Kane, G. Bielmeier, Y. S. Hoare, R. J. Kaver and M. Z. Hussain. Observation of unconventional quantum spin textures in topological insulators. Science 323, 919 a 922. Bibcode, 2009 Sci. 323 919 H doi, 10.1126/Science 1167733. Retrieved 2010. N. Reed and Subers Sachdov, Large N expansion for frustrated quantum antiferromagnets, Phys. Rev Let 66 1773, Xiaogang Wen, Mean Field Theory of Spin Liquid States with Finite Energy Gaps, Phys. Rev B 44 26 64. Further reading, Hussain, M. Zayed. Kane, Charles L. Topological Insulators. Reviews of Modern Physics 82, 3045. AR Ziv, 1002.3895. Bibcode, 2010 RVMP. 82.3045H doi, 10.1103/Rev Mod Phys 82.3045. Kane, Charles L. Moore, Joel E. Topological Insulators. Physics World 24, 32. Kane, Charles L. Topological Insulator, an insulator with a twist. Nature 4, 348. Bibcode, 2008 NatPH. 4348K doi, 10.1038/NPHYS 955. Whites, a Topological Insulators, Physics on the Edge. Science News. Brumpf, G. Topological Insulators, Star Material, Nature News. Nature 466, 310 a 311 doi, 10.1038/466310A. PMID 20631773. Murakami, Shuichi. Focus on Topological Insulators. New Journal of Physics. Unregistered trademark S. A Topological Insulator. Topological Insulators, by Joel E. Moore, IEEE Spectrum, July 2011.